Hello kids, hope you are enjoying this nice weather and glad it is finally warm, and welcome to our last video of the year. Can you believe it? Your homework is in the book, 19 through 37 odd. Shouldn't be too taxing, I don't think. And again, if you want to pause the video to do this warm-up and then check back to see if you've done it right, that would be fine, but I want to practice converting to polar form. So notice we call this rectangular or standard form. To convert this, we need r and we need theta. And we have to be careful with theta as to what quadrant we're in. Right, so first think about this again on our real and imaginary axis, not called the Cartesian plane, remember called the Arngard, I don't remember how to pronounce his name, plane. So if I go out a radius of 2 and down 2i, out on the reals to 2 and down on the imaginary, here is my radius. And that radius, right, is 2 squared plus 2 squared, which is the square root of 8. So my radius is 2 root 2. And I have to think about inverse tangent of, what is that going to be? -1, right? Which makes sense because I'm in quadrant 4. So again, I want the positive angle that gets me there. So this is r cis, 2 root 2, 7 pi over 4. Okay, you want to do the same with this. R theta and what quadrant I'm in, and I hope you can see with the real part being negative and the imaginary part being negative, you are in quadrant 3. This is inverse tangent of 1 over root 3, right, which is a pi over 6 issue. So being pi over 6 in the third quadrant, I need 7, and this is this 25 times 3, which is 75, plus 25 is 100, square root of 100 is 10. So this is 10 cis 7 pi over 6. Converting to rectangular form, need your speed trig skills, right? Cosine 2 pi over 3, right? Cosine pi over 3 is 1/2, but cosine in the second quadrant is negative. Sine of pi over 3 is root 3 over 2, but in the second quadrant is positive. And then multiplying by 10. Right? Looks pretty similar, doesn't it? See what's going on there? This one is in quadrant 2, right? I have the same same values. So I have the same radius, 10, but I'm in the second quadrant. How about the next one? Cosine and sine of pi over 4 is root 2 over 2. But 7 pi over 4 is in which quadrant? Fourth quadrant, so cosine is positive and sine is negative. So this becomes 12 root 2 minus I 12 root 2. And with a positive real and a negative imaginary, that's in quadrant 4. Check. Now what the hee-haw is this? Right? Taylor series, hello, throwback to the last unit. So I want you to think of this as a composition. So you should be thinking about e to the x first. That Taylor series is 1 plus x squared over 2 factorial Oh, and they only wanted the first 6, so I should write approximate 1, 2, 3, 4, 5, and 6. So that's e. How do I get e to the ix? Right, that's just a composition. So e to the ix just means replacing every x with ix. So that's 1 plus ix plus ix squared plus ix cubed but let's use our I pattern, right? Our I pattern knowledge to rewrite some of this, right? Isn't this I squared, which is negative 1, I cubed, which is negative I to the 4th, which is 1, and I to the 5th, which is the same as I to the 1st, right? So how can I write this? Oh. Minus, right? Because I squared is negative 1. And then I cubed is negative I, isn't it? But I to the 4th is just 1. And I to the 5th we said was the same as I to the 1st. Okay, so kind of cool there. Using Taylor series and writing e to the ix as an infinite polynomial. I know I only wrote 6 terms, which is why it's approximate here, but an infinite polynomial-ish, right? With i's in it. All right. Now I do want you, even those of you who shall remain nameless may not be taking notes, please write this down, at least from your warm-up, because we're going to refer to this later. All right, so we're going to do some arithmetic, right? Some basic operations in polar form. So we're going to multiply, divide, and exponentiate complex numbers in polar form. And we're going to go back and forth between polar and rectangular, complex rectangular form. So firstly, multiplying and dividing. So what if I have 2 random complex numbers in, I think you can see polar form already, right? So these were given to me in polar form, or somebody transformed them into polar form. And I have 2 different complex numbers, so 2 different radii and 2 different angles. So to multiply them, since everything's multiplication and multiplication is commutative, I'm going to go ahead and move these around and multiply those 2 together first. Then I'm going to distribute. Cosine 1 times cosine 2. And then look what happens here. I sine theta 1 times I sine theta 2. What happened to the i's? I times positive I times positive I is positive I squared, which is -1. There it is. Then the next thing I'm going to do is distribute, right, the cosine 1 to I sine theta 2. That's right here. Cosine 1 sine theta 2, and I just factored the I out front. And I sine theta 1 multiplied cosine theta 2. Okay, and everything was positive, and I just factored my I out front. Now take a look at those, right? Hello, first semester. Do you recognize that? Cosine, cosine, minus sine, sine. That is the sum identity, sum of two angles identity. Whoa! Say what? And then look at this. Sine, cosine plus cosine, sine. Well, that is the sine sum identity. What? So what does this say that we can do, right? If you want to multiply two complex numbers, look what happens. You multiply the radii, but you add the angles. Pretty simple. And the same, right? An analogous relationship is with division. So given two polars that you want to multiply, multiply the radii, add the angles. For division, divide the radii and subtract. And again, remember, it is a rule of thumb to not have, right, tradition not to have a negative angle in there, right? So just use your coterminal knowledge and get me a positive one. So, for example, evaluate this product, but you can leave your answer in polar form. You don't have, whoops, you don't have to put it into rectangular form. So using our formula, what are we going to do? We're going to take the two radii, multiply them together, and we're going to take the two angles and add them. And notice I just did an example in degrees. It is not common, you know, both of these, degrees and radians, are more common. I stay in radians simply because you need radians in calculus. Silly physics uses degrees more. Mr. Getz is glaring at me. Can't do physics without math, Mr. Getz.
Yes, that is true.
All right, so I then asked you to graph the two original complex numbers on this plane. So without being in rectangular form, I can still do this, right? 5, radiate out 5 units, and rotate 50 degrees. See the relationship with polar graphing? Right, because it's cosine, sine. Then let's do 7, rotate out 7. I'm sorry, radiate out 7. but only go 20 degrees. Now graph the result. What does the result look like? The resultant multiplication has a longer radius, doesn't it? You multiplied them. So go all the way out here to 35. I'm going to shrink my scale a little bit. And rotate 70. So whoop. Again, my scale is probably way off, but multiply the two radii, add the two angles. Done and done. So what about these? Now again, there's 3 problems. See if you want to pause the video and do this yourself or follow along with me. Notice though that I've asked you here to put this in standard form. Here, these, you can leave your answer in polar form. So what does this look like? Right? So what is that but now I have to put this in standard form. So but what is cosine of pi and sine of pi? So this just ends up being -6. Well, what the heck? You're telling me if I radiate 3 and rotate to 2 pi over 3, whoops, I'm sorry. Radiate 3 and go pi over 3. Radiate 2 and rotate to 2 pi over 3. That result is here at -6 in rectangular form, right? Because -6 is -6 plus 0i, so you go out to -6, and that's the same as radiating 6 and rotating pi. Wow. All right, I wanted you to see how sometimes these problems are presented, right? They tell you I have a complex number in polar form, they call it z, they call this other one w, and they want you to evaluate z over w. It's just a comma, me trying to do English there. So what do I have to do here? This is a simple formula. Right, so all I have to do here is divide 15 and 5, and I get 3. And 75 minus 100, though, is what? 75 minus 100 is negative. Right, so please don't leave a negative there. So think about what this means. So 15 cis 75 is right there. 5 cis 100 is maybe right there, right? So dividing them, I get a shorter radius of only 3. And going down negative 25 lands me there, right? Probably even a little bit higher. Right, that's negative 25. Please tell me what the positive angle to that is. Right, 360 minus 25. And that's just so we don't have to put the parentheses there, right? With the positive, we can just, because it would look so weird to have cis negative without parentheses. So this is just the preferred, right? There on a free response or where you're writing an answer, there may or may not be a point with the positive result, but certainly in any multiple choice, you're not going to see a negative. Now look at the next problem. The next problem looks like I just copy and paste it, didn't I? But do you see what the deal is here? Order of operations, you got to square that first. So this is actually a multiplication and a division problem in one, which is a great test question because I'm testing two objectives in one problem, right? So let's take care of the multiplication first. So I have 15 cis 75 times 15 cis 75. So z squared is going to be what? Right? Square 15 to get 25 and double 75 to get 150. Now I'm going to divide that by w. Whoops. So 225 divided by 5 is 45. 150 subtract 100 is 50. Cool. Now, I do want you to recognize something that happened here. We squared 15, and since 75, and we said 75 plus 75, but isn't that 2 times 75 degrees? And couldn't I rewrite this as what's happening here? Whoa. Well, hello, Demoivre. I wish I remembered his first name. I want to say Abram, but I don't know if that's right. Demoivre has a theorem that you are responsible for. So the theorem extends what we just did. If you have a number in polar form that you are raising to the second power, right? So you have r cis theta times itself. As we saw before, this is what happens. You end up, you square, right, the square of the radius, and then going back before this, right, what I have is just using the distribution of binomials to multiply binomials, right, using the same pattern. I get cosine, cosine minus sine, sine, but isn't that cosine squared theta minus sine squared theta? Whoa, hey now. That's another trig identity. It's the cosine, right, double angle cosine identity. Woot! And then look what happens here. Factoring out the I get sine theta 1 cosine theta 1 plus sine theta 1 cosine theta 1. Isn't that two of those? Hey now! That is sine double angle. Holy guacamole! That is de Moivre's theorem. I don't know why my thing is freaking out. I really just want to erase my pen. What is happening? Well, whatever. Sorry, I can't erase it right now. There is de Moivre's theorem. So this works not just for squaring, but he proved, right, that this goes on and on as long as n is an integer. Then it is true that raising a complex number to a power is equal to raising the radius to the same power and then multiplying theta by that n. So you have n here. Exponentiate the radius, but multiply the theta. Crazy, whack, funky. Eh? That de Moivre. So let's try these examples, right? So I want, first problem here, I've given you a number in complex form. Oops, I dropped the 2, sorry. There's supposed to be a 2 in front of this. But I want the result in rectangular form. So using de Moivre, I am going to raise the radius to the power of 5, but I am going to multiply pi over 6 by 5. And I get 32 cosine 5 pi over 6, right? Cosine of pi over 6 is root 3 over 2, but cosine is negative in the second quadrant, plus a half. Sine of pi over 6 is a half, but with 5 pi over 6, I'm in the second quadrant where sine is positive. So this is negative 16 root 3 plus 16i. Crazy, right? Now look at the next example. They want me to find, look, there's no polars in this. This is rectangular. W is in rectangular or standard form. And they want my result in rectangular form. So what the heck? Well, if I'm in rectangular form and I want W raised to the fourth, I need to raise this to the fourth, which means I write it 4 times and multiply, right? You cannot distribute the fourth to each one of those, right? That is not how you work in rectangular. It is not true that x plus y to the fourth does not equal x to the fourth plus y to the fourth. That is not true. You would have to actually write out x plus y times x plus y times x plus y times x plus y. But what if I decide to transform myself into polars because I recognize that raising polar values to powers is much simpler. I don't want to do this, right? So what if I decide to put this into polars? And to put this into polars, I need the radius, which is the square root of 2 over 2 times the square root of 2 over 2. I'm sorry, squared. I like to use this form here. I think it makes my math easier, which is what? 1/2 plus 1/2 square root, but that's 1. So my radius is equal to 1. And then I need to worry about what quadrant I'm in. Negative x, positive y is quadrant 2. So the inverse tangent of -1, or again, I can just care, I'm in the second quadrant, so the inverse tangent of 1 is pi over 4. And I want to be in the second quadrant, so that is 3 pi over 4. So I have in polar form now, if I take what's in the red parentheses, in polar form, I have 1 cis 3 pi over 4, and I am asked to raise that to the 4th power. Well, isn't that just 1 to the 4th cis 4 times 3 pi over 4? But the 4's cancel out. So I end up with 1 cis 3 pi. But isn't that the same as using coterminal? 3 pi is the same as pi, isn't it? So that's cosine pi plus I sine pi. But wait, sine pi is 0, so that's just cosine pi, which is -1. What the hee-haw? Crazy. Let's look at your calculator. And let's type that in. Square root of 2 divided by 2 plus, oh sorry, that's a negative, isn't it? Plus I square root of 2 divided by 2. What the hee-haw? I forgot to raise it. That's just what that's equal to, right? I forgot to raise that to the 4th power. -1 minus 0i. Whoa, what the hee-haw? Hey, do you remember this problem from our review handout in the last video? Right, and I told you that you would have to multiply it all out, right? But then I showed you how to put this into your calculator instead of multiplying it all out, because I knew I was going to give you a shortcut today. And if you remember when we used our calculator yesterday, or previous lesson, we got 64i using the calculator. So now, again, here is the power of polars. No one says to me that I need to use polars on this, but I recognize rectangular form of a complex number being raised to a power, and I say, Demoivre, come over here. Come over here and help me out. Right? So first I turn this into polars. So what is this going to be? 2 squared is 4, root 3 squared is 3, so 4 times 3 is 12, plus 2 squared, which is 4, which is 16, so my radius is 4. I'm in the first quadrant, so I am doing inverse tangent of 2 over 2 root 3, so that's 1 over root 3, so theta is pi over 6. So turning this into polars, I have 4 cis pi over 6. Right? Demoivre says that is 4 cubed cis pi over 6 times 3. So that is 64 cis pi over 2. Cosine pi over 2 is 0. Sine pi over 2 is 1. So this is 64i. OMG. Sure, if I have a calculator, I don't need Demoivre. But what if your calculator is taken away from you? If your calculator is taken away from you, which Demoivre didn't even have right? He didn't have a choice. He didn't have any calculator. In order to evaluate this, you would have to multiply this out. And you might want to do that and show that there's a third way. You can use your calculator, you can use Demoivre, and you can actually use algebra, and you will get 64i if you do your algebra right. Woot! Woot! All right. Now, an application of this that we're not going to get to, that we would have, but it's okay, is this Demoivre is used to find the non-real roots of, for instance, right, something like a cubic that only has one real x-intercept, okay? So something cubed, right? I can use Demoivre to do that. And then the actual, like, engineering application, this is all in communications, right? Using polars, right, makes the communications algorithms and the math and the engineering that you need to do with your cell phone, right? Why cell phones work and satellites and GPS and all of that. You use polars all the time. Differential equations, this is gonna come back again. Higher level math, you're gonna deal with this, right? And in differential equations, you'll certainly see Demoivre again, and then if you go forward in engineering. All right, let's go back to plotting here. So I'm giving you a particular complex number in polar form, right? Here's r cis theta. But I'm giving you different values of theta, and I'm asking you to plot on the imaginary, or excuse me, the complex plane. So if you plug in 0 here, cosine of 0 is 1, but sine of 0 is 0, so the I drops out, and you just get 1, and let's plot that. Right? Z is 1, and theta is 0. How about pi over 4? Pi over 4 is root 2 over 2 plus I root 2 over 2 all times 1. So I'm going to go, right, Z, I'm going to go out, right, pi over 4 and a radius of 1. How about pi over 2? Where at pi over 2, cosine is 0, right? So I have 0, so this is technically 1 plus 0i, and this is 0 plus 1i. I think you can see what's going to happen here, right? In the second quadrant, cosine is negative. So I'm going to be here, and again, each one of these has a radius of what? Pi, cosine is negative 1, but sine is 0. Right? Radius of 1, rotate pi. Three pi over 2, cosine is 0. Sine is negative 1. My radii are getting longer and longer, aren't they? Cosine is positive in quadrant 4, but sine is negative. I think I see a little bit of a pattern here, don't you? The radius is always 1. And each one of these points is, right, cosine, I sine. But again, the I just tells you to go up, doesn't it? Up or down, positive I or negative I. The length that you're going over 1 and up 0. You're going over root 2 over 2 and up root 2 over 2. Right? You're going over none and up 1. So each one of these points has a length, a horizontal length, and a vertical length of cosine comma sine. And if you connect all of them, oh my goodness, not only do you get a circle, which circle do you get? The unit circle, baby. Right? Right? I mean, woot woot. Radius of 1, cosine, sine gives me the points on the unit circle. OMG. Well, if that wasn't cool, it's amazing. It's so great that this is the last lesson because this stuff is freaking cool. Watch this. Hi, Taylor. What up? So remember the warm-up? The Taylor connection? Right? So here is a complex number in polar form, but it's got cosine and sine inside of it, right? So what if I make, what is the Taylor series for cosine? Right, remember cosine is even, so it has the even power, so it has x to the 0 minus x squared over 2 factorial plus x to the 4th over 4 factorial, and then that pattern continues, right? And what was sine? Sine isn't even, it's odd, right? So you have x to the 1st minus x cubed over 3 factorial plus x to the 5th over 5 factorial. So I have a representation for cosine. I have a representation for sine, but I don't really want sine. What do I want? Oh, but I learned how to do that, didn't I? I have sine already, so what if I want I sine? Just multiply everybody by I, don't I? So this isn't a composition, this is a multiplication. Multiply everybody times I. Well, way back in AAF, I told you that you can add polynomials together, can't you? Well, you can add infinite polynomials. What if I want to take cosine and add it to I sine? What do I get there? Well, let's see. I want to add all of these to all of these, and I think I will go ahead and put them in power order, right? I'm going to start over here because I've run out of room, so I'm going to write 1 plus ix minus x squared over 2 factorial minus ix cubed over 3 factorial plus x to the 4th over 4 factorial plus x to the x to the 5th over 5 factorial. And I could keep going as long as, right, I would just keep going with each one of these. Wait just a second, though. Whoa. Now, I haven't multiplied by r yet. But couldn't I say that right? But wait. Look at your warm-up. Look at the third problem of your warm-up. What is happening? My world is exploding. This is amazing. Naturally out of investigating math, what happened? What happened? E happened. Oh my gosh. That's e to the ix is the same thing as cosine theta plus I sine theta. They are the same. You just proved it. So e to the ix is the same thing as what? That's called Euler's equation. Hello, Euler. R times, right, because I put an r out here, r times e to the I, oops, I made this should be a theta, to the I theta is equal to r cosine theta I sine theta. Whoa. Whoa! I mean, just naturally. E happened naturally. That's why it's called the natural number. Euler named the natural number after himself. Hey, what if you let r in Euler's equation be 1 and theta equal pi? So 1 times e to the I pi is 1 cosine pi plus I sine pi, but remember sine pi is 0, so this part is going to go away. So e to the I pi is equal to what? 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 E to the I pi. It's up and it's good. I mean, right? This is so crazy. So crazy. Math is so cool. I hope that you are well and safe, and I hope to see all of you at some point next year. I hope that some kind of healing can happen physically, emotionally, for all of us, for our country, and I hope that there has been a little bit of enjoyment and excitement about mathematics through this year that inspires you. I know you have to take math classes, but there is so much in mathematics that is really cool just because it's cool, not for engineering and not for my transcript and not whatever. There is so much that is just beautiful and cool, and I hope that you have seen just a little bit of this and maybe inspires you to see and explore a little bit more. Have a wonderful rest of your week, the wonderful rest of your summer, and again, I hope very much to see all of your faces at some point next year. Take care. I miss you. Be safe.